Okay, let's unpack this. Have you ever wished for, like, a shortcut to truly grasp the most complex and hotly debated ideas shaping our world?
Hmm.
Today, that's exactly what we're doing. We're embarking on a deep dive into the fascinating realm of controversial scientific theories.
Yeah.
We're pulling the most important nuggets from a fantastic article that lays out 10 really intensely debated ideas spanning centuries and disciplines.
Right.
Our mission is, well, to ensure you walk away feeling incredibly well informed with some genuinely surprising insights to mull over.
And it's interesting, isn't it? We often think controversy, and it sounds negative.
Yeah,
But
definitely.
in science, it occupies this incredibly dynamic and frankly crucial space. These aren't just, simple hypotheses.
Yeah.
They're vigorously debated, not just within labs or universities, but across cultural, political, ethical,
Yeah.
often religious arenas too.
hmm
Is it really where the boundaries of what we know get pushed and interrogated most rigorously?
Absolutely. Think of controversy as the leading edge of inquiry, right? The very place where intellectual progress frequently emerges. It's where dissent often fuels discovery. So, get ready, because we're about to explore some of the battles that has shaped and, well, continue to shape our understanding of the universe.
Sounds good. Where do we start?
Let's begin with a true archetype of scientific revolution, the heliocentric model.
Ah, the classic.
For centuries, the Earth-centered or geocentric model, championed by ancient thinkers like Ptolemy and later deeply intertwined with church doctrine, it completely dominated Western thought.
And when Nicholas Copernicus, back in the 16th century, proposed that the Earth actually revolved around the sun, well, it wasn't just an astronomical tweak.
No, far from it.
He was fundamentally upending a whole cosmological and even spiritual worldview, where humanity was literally at the center of everything.
Right.
The institutional resistance, the philosophical implications, they were immense.
And then came Galilei, early 17th century, his groundbreaking telescopic observations, like discovering Jupiter's moons, orbiting another planet, or seeing Venus go through phases, just like our moon.
Yeah, powerful stuff.
That provided really strong empirical evidence for Copernicus's model. But it wasn't exactly a smooth road for him, was it?
Oh, far from it. His findings directly challenged the established order. I mean, it led to his eventual condemnation by the Roman Catholic Church during the Inquisition.
Hmm.
Galileo's defiance, it really symbolized that profound tension between empirical science and, well, ecclesiastical authority.
Yeah.
And while it's universally accepted today, its legacy as a battleground between innovation and orthodoxy that ensures its controversial status in the history of ideas.
It really does.
What's often overlooked, too, is why the geocentric model held on for so long. Part of it was observational.
How so?
Well, the heliocentric model predicted stellar parallax stars should appear to shift slightly as Earth orbits the sun. But the instruments back then just weren't sensitive enough to detect it.
Ah.
So the common sense view of a stationary Earth was actually pretty compelling based on what they could see, or rather couldn't see.
Okay, here's where it gets really interesting. Moving forward a few centuries, we hit Charles Darwin and Alfred Russel Wallace's theory of evolution by natural selection.
Darwin.
Published in Darwin's On the Origin of Species in 1859, this theory proposed that species evolve gradually over time through variation and differential survival.
And this theory absolutely revolutionized biology.
Yeah.
It created the foundation for modern genetics, ecological science, pretty much everything.
Yeah.
However, it immediately met severe opposition, particularly from religious communities who saw it as a direct challenge to, well, divine creation.
Right. And that led to some major clashes.
Huge cultural conflicts, like the infamous 1925 Scopes trial in Tennessee, remember, where teaching evolution in public schools actually became a legal offense.
Wow. So even though it's scientifically solidified now, I mean, through modern genetics, the fossil record, molecular biology, it still sparks debate in some circles today.
Precisely. Evolution continues to draw opposition in educational policy debates, especially in regions where religious conservatism strongly shapes the curricula. But what's often overlooked is how the very process of scientific inquiry around evolution has been sharpened by these challenges.
How do you mean?
Well, the need to provide ever more robust evidence, for example, directly pushed fields like molecular genetics forward, things Darwin couldn't have dreamed of.
Right.
And that new evidence overwhelmingly supports his original insights. So it's a kind of powerful example of how skepticism, even if it's ideologically driven sometimes, can inadvertently strengthen scientific rigor.
Okay, let's shift gears. A more recent and maybe somewhat infamous controversy, cold fusion.
Ah, yes, Fleischmann and Pons,
Uh,
1989.
exactly. These chemists announced they'd achieved nuclear fusion at room temperature, a feat that, I mean, if true, could have solved the world's energy problems overnight.
The claim sparked an absolute international frenzy. Labs everywhere scrambled to replicate the findings. But the vast majority of attempts failed. They couldn't reproduce the claimed excess heat reliably, and crucially, they couldn't detect the expected nuclear byproducts.
It's like high-energy neutrons.
Exactly, the kind you always get with true fusion reactions. So this led pretty quickly to accusations of poor methodology, premature publicity,
Yeah.
and the scientific community largely deemed cold fusion invalid.
So it's often cited as this classic cautionary tale in science. But I wonder, was the scientific community maybe too quick to dismiss it entirely, or was the initial backlash totally justified?
Well, it's a complex question. The initial backlash was largely justified, I think, given the lack of consistent verifiable evidence, and especially the absence of those critical nuclear signatures.
That extraordinary claims.
Require extraordinary evidence,
Yeah.
exactly. But this wasn't just a blip. Cold fusion, or low-energy nuclear reactions, as it's often called now,
Mm.
it fundamentally changed how academic institutions and funding bodies approach these kinds of extraordinary claims. It created a lasting chill on certain types of exploratory research. Because small groups of researchers still investigate anomalous fusion phenomena, just under different names. But with way less funding and mainstream attention, it really highlights that difficult balance, between healthy skepticism and potentially stifling new, unconventional ideas.
Okay, now back to the cosmos, but on a much, much grander scale. Since the mid-20th century, cosmology's been grappling with a fundamental question. What explains the way galaxies rotate?
Right, the rotation curves.
Observations of spiral galaxies show their outer regions spin much faster than our current understanding of gravity, and the visible mass says they should.
And what's fascinating here is you've got two main competing explanations.
Okay.
One suggests there's a bunch of unseen mass out there, what we call cold dark matter. Vera Rubin's pivotal work on those galaxy rotation curves lent really strong support to this idea. The other camp says, well, maybe we need to revise our fundamental gravitational equations. That's modified Newtonian dynamics, or MOND,
Yeah.
tweaking gravity at very low accelerations, as Mordechai-Milgram suggested.
So it's either an invisible, something we just can't detect yet, or a fundamental change to how we understand gravity itself. Wow, those are two pretty huge implications.
Exactly. And while dark matter is still the dominant paradigm, it fits with a lot of other observations beyond just galaxy rotation, like the structure of the cosmic microwave background.
The echo of the Big Bang.
Right, and the large-scale clustering of galaxies. But it has never been directly observed. Despite decades of trying with underground detectors, collider experiments, nothing conclusive. Meanwhile, MOND, while it elegantly explains galactic rotation without dark matter, it struggles to account for things like galaxy clusters or that cosmic microwave background without adding its own exotic components.
So neither is perfect.
Exactly. The debate persists because neither theory is perfectly complete. And that makes it one of the most fundamental puzzles driving cosmology research today. It's a big one.
Okay, shifting gears again. Few scientific controversies have been as emotionally and, frankly, politically charged in recent memory as the origins of the COVID-19 virus.
Yeah, that's certainly true. While the predominant theory still points to a zoonotic spillover, the virus jumping from animals to humans, possibly through those wet markets in Wuhan, alternative theories claim the virus could have accidentally leaked from a laboratory.
And initially, discussing the lab leak idea was often, well, dismissed, right, as a conspiracy theory, especially early on.
It absolutely was, particularly in the early days of the pandemic.
But that perception definitely shifted, didn't it? What changed?
It did shift as more information surfaced, including questions about transparency from certain institutions, questions about biosafety standards at specific research facilities, and just the timelines of early cases.
Right.
The lab leak hypothesis regained a degree of scientific and journalistic legitimacy. It became something researchers felt they could discuss more openly.
So where does it stand now?
Well, today, major health organizations like the World Health Organization and various intelligence agencies, they remain divided. Most scientific reports still favor natural origins, but they simultaneously call for more data, more transparency. This whole controversy, it really underscores the immense pressure on scientific institutions during global crises, and it highlights how political environments can deeply shape scientific discourse and, importantly, public trust.
Okay, let's talk about how scientific knowledge can get really distorted in the public imagination. A prime example, the chemtrails conspiracy theory.
Ah, chemtrails, yes.
This theory alleges that governments or some shadowy organizations are releasing harmful chemicals into the atmosphere using aircraft, usually for nefarious purposes.
And it actually stemmed from something completely normal.
Yeah.
Contrails, which are just water vapor from jet engines condensing into visible clouds at altitude. Simple physics. But the chemtrails narrative somehow took off in the 1990s and then absolutely flourished with the rise of social media, leading to these elaborate claims about weather modification, population control, you name it.
Despite being debunked repeatedly.
Oh, extensively debunked by atmospheric scientists, agencies like the EPA. But a significant segment of the population remains convinced.
And it even gets amplified by some politicians, which must make countering it even harder.
It certainly does. While there's absolutely no scientific basis for chemtrails, their staying power reflects these broader societal anxieties, doesn't it? About environmental vulnerability, maybe unchecked technological power, institutional secrecy.
Yeah, that makes sense.
It's a powerful case study in how misinformation takes root, often tapping into existing distrust. And it shows the immense challenges of scientific communication in today's fragmented public sphere.
It really does.
It highlights that just presenting the facts isn't always enough to change deeply held beliefs, especially when those beliefs connect to larger anxieties or worldviews.
Okay, another area where science and belief systems often clash fiercely is around the theory of intelligent design.
Right, ID. This posits that biological complexity, especially down at the molecular level, points to a purposeful designer rather than purely random evolutionary processes.
So it's kind of a newer version of older arguments. Sort of. It resurfaced from the ashes of earlier U.S. creationist movements, but strategically rebranded its religious origins as a supposedly scientific perspective. This really intensified debates over science curricula in public schools.
And proponents like Michael Behe, they talk about irreducible complexity.
Exactly. His argument is that certain cellular mechanisms are so complex, like a mousetrap, he famously used that analogy, that they couldn't have evolved gradually, because removing any single part would make the whole thing non-functional.
And this led to some landmark legal battles, didn't it?
It did. The big one was Kitzmiller v. Dover Area School District in 2005. That trial really underscored the national friction this theory causes.
What was the outcome?
The court meticulously examined the claims and concluded that intelligent design is intrinsically religious, not scientific, and therefore it's unconstitutional to teach it as science in public schools.
So even though ID lacks empirical support, it doesn't offer testable predictions, which is a hallmark of science. It still retains substantial cultural influence. It really demonstrates how these ideological boundaries become battlegrounds for educational policy.
Yeah.
The controversy isn't really about whether life is complex, obviously it is, but whether the explanation for that complexity must invoke a non-naturalistic designer. Science seeks natural explanations.
Let's turn to a controversy where, wow, immense scientific potential meets really profound ethical dilemmas. Embryonic stem cell research.
Ah, yes. This involves using cells derived from early-stage human embryos, blastocysts, usually to understand development and potentially cure debilitating diseases, things like Alzheimer's, spinal cord injuries, diabetes.
The potential sounds incredible.
The scientific promise is immense. It offers whole new avenues for regenerative medicine. However, the ethical landscape remains, well, fraught.
Because of the source of the cells.
Exactly. The central moral concern revolves around the destruction of human embryos in the process. Opponents equate this with the termination of potential human life.
And this debate really blew up, didn't it?
It reached its zenith in the late 1990s and 2000s. We saw shifting U.S. federal policies under successive administrations, Clinton, Bush, Obama, which really reflected the nation's deep moral ambivalence about it.
So even with that incredible medical promise, this remains a deep moral and ethical debate for many people. How has that tension evolved over time?
Absolutely. While regulatory frameworks now allow for such research under specific guidelines, and newer techniques have emerged like induced pluripotent stem cells or iPSCs.
Like reprogramming adult cells.
Exactly, which offers alternative approaches.
Yeah.
Still, public disagreement over the fundamental moral status of embryos, essentially. At what point an embryo gains the rights or ethical considerations of human life that ensures this controversy remains active in bioethics discussions?
It really does.
It's a classic example of where scientific advancement pushes directly against deeply held societal values, creating this necessary ongoing conversation about the boundaries of research.
Okay, next up. The rapid evolution of artificial intelligence. This has brought forth one of the most expansive and frankly urgent scientific controversies of our time.
Definitely. AI. Initially, it was greeted with widespread optimism, right, for its potential to revolutionize healthcare, finance, transportation, learning, everything.
But then the concerns started growing.
Yes, significant concerns, centering on critical issues like algorithmic bias, where AI systems perpetuate or even amplify existing societal biases. Also, automation-induced unemployment, surveillance risks, and maybe most acutely the deployment of autonomous weapons, lethal autonomous weapon systems, or law abuse.
Scary stuff.
These risks have amplified global anxiety. You see prominent figures like Elon Musk, various research institutions calling for regulatory oversight, strong ethical frameworks. Others, though, warn against sensationalism that could stifle crucial innovation.
So it really feels like this race to balance the incredible possibilities of AI with its potential threats. What are the core tensions here, would you say?
The core tension is navigating that precise balance. How do we lock in beneficial designs, ensure AI serves humanity, while effectively curbing the potential threats, especially from systems that might eventually surpass our own cognitive abilities?
That's the million-dollar question.
It really is. Ongoing debates over, how fast to regulate, how to get global cooperation, even how to define safe AI, it all underscores the immense complexity.
Yeah.
This isn't just a technical challenge, it's a profound contemporary dilemma. It forces us to ask how we balance this incredible technological possibility with the imperatives of human rights, economic stability, collective responsibility, all while the tech itself is still developing at breakneck speed.
Wow. Okay, our final controversial theory takes us beyond Earth, the search for extraterrestrial life.
SETI and related fields.
Yeah. Once pretty much the sole province of speculative fiction, it's become a legitimate scientific endeavor, yet it remains highly controversial, certainly within parts of the scientific community.
Absolutely.
Yeah.
You have theories like panspermia, the idea that life could have originated elsewhere in the universe and arrived here on Earth via comets or meteorites. That fundamentally challenges our understanding of life's origins.
Right.
More recently, you have claims like those by Harvard astrophysicist Avi Loeb regarding anomalous metal spheres found in the Pacific, potentially linked to alien technology. That's captured huge public imagination, but also significant scientific skepticism.
And then there are the declassified government UFO files, or UAP files now. That only adds to the intrigue, right? Makes it even harder to separate the science from the speculation.
They absolutely do. They fuel both genuine intrigue and, unfortunately, a lot of misunderstanding. While most scientists rightly call for incredibly rigorous standards of evidence, meaning clear, repeatable, verifiable data,
Yeah.
public fascination with the possibility of intelligent alien life just continues to thrive. The controversy here often lies in that extremely high burden of proof required for such extraordinary claims.
Understandably so.
Right. The implications, if proven, would be just immense for theology, philosophy, biology, our entire sense of place in the cosmos. Which is why the topic remains both at the edge of mainstream science and right at the heart of public discourse. It constantly pushes us to question how we define evidence, how we accept evidence for phenomena that challenge our most fundamental assumptions.
So after diving into these 10 quite different controversial scientific theories, what does this all mean for us? It seems clearer than ever that controversy isn't just a negative force in science.
Not at all. What's truly fascinating here is how controversy actually plays an indispensable, maybe even essential role.
How so?
Well, it stimulates deeper peer review. It encourages scientists to develop more robust methods. It invigorates public engagement with complex, important questions. And though it can feel antagonistic sometimes, the tension it produces is often the very crucible in which better theories are forged. It helps refine our understanding, not just confirm what we already think we know.
It's a powerful reminder that knowledge isn't static, is it? It's not like a finished book.
Absolutely not. Ethical debates ensure science stays connected, hopefully, to human values. Paradigmatic challenges remind us that all scientific knowledge is provisional. It's open to revision.
Yeah.
Controversial theories serve as both warnings and guideposts. They signify the boundaries of what we currently know and maybe even what we are. They urge us forward. Even as they expose our current limits, they really prove that science is this living, breathing, constantly evolving conversation.
That's a great way to put it. As science advances, controversy will undoubtedly remain one of its sharpest tools and maybe one of its most vibrant mirrors.
Well said.
So it makes you wonder, what new controversies are waiting just around the corner? What ideas will reshape our understanding of the world next? And what role might you, listening right now, play in shaping those debates, simply by staying informed and asking critical questions?
Hmm.
We invite you to keep exploring, keep questioning, and definitely keep diving deep with us.